In this video you will learn how to derive the formula for the parallel connection of resistors from Kirchhoff's first law and from Ohm's law. I'll also show you why each additional parallel resistor makes the total resistance lower in the network and thus increases the amount of current flow. And finally, as always, there's going to be a summary of the most important facts from the video for you at the end, so stay tuned. And my name is Andreas from The Fearless Engineer, and here we go. Now let's start with shortly discussing the motivation behind making this video. You might have known already, if you have watched one of my previous videos before, that if you connect more than one resistor in parallel to a voltage source, that the current from the source increases. And the goal of this module is to explain this behavior of the circuit, this relationship, and also to derive a formula for the parallel connection of resistors. And in order to get there, we have a four-step approach. In the first step, we're going to conduct a measurement of current and voltage to compute the total resistance using Ohm's law in a simulated circuit. In the second step, we're going to combine the junction theorem by Kirchhoff and Ohm's law. In the third step, we're going to exploit the voltage equality between devices or components which are connected in parallel and which share two electric potentials, one before and one after the components. And fourth, the last step is to find an explanation, an alternative explanation approach despite or in addition to the mathematical derivation which we have performed until step 3, which can explain this behavior. And the concept we're going to use is we're going to look at the cross-sectional area of a resistor, which takes into account the geometrical shape of the resistor, which we have talked about before in other videos when we introduced this concept of resistance depending on the length and material properties and the cross-sectional area of a resistive body. Now in the first step, let's take a look at the actual circuit. What you can see here on the left is a voltage source configured to 10 volts. Then we have 3 resistors connected in parallel to each other. The first with 328 ohms, the second and third with 3.27 kilo ohms. And as you can see from the simulated currents here, the current through the first resistor is the largest, which is as expected because the current tends to take the path with the least resistance, and as this resistor here is by far the smallest, the current is the largest. As you can see, it's a factor of 10 between the currents and a factor of 10 between the resistance values here. And we are now looking at the voltage drop across these components, as well as the current flow in total, which leaves the voltage source. And as you can see here, by using Ohm's law, by dividing 10 volts by 35.82 milliamps, we get a total resistance of this combined circuit here of 279.17 ohms, which is smaller than the smallest individual component. So this is the key observation here. The resulting total resistance of a parallel combination of resistors is smaller than the smallest individual resistance in the entire circuit in this parallel configuration. And in order to understand this, to also derive the formula to compute this, we have to reshape the circuit a little bit just to make things more visible or more clearly visible. And in order to use the junction rule by Kirchhoff, we need to reshape one particular part of the circuit, which you can see here on the right side or on the left side. This is the original circuit consisting of these 3 resistors which are connected in parallel. And as you can see, we have 4 junction points in total, but between these 2 junction points here at the top and the 2 at the bottom, there is no no component. So this is an ideally connected line with 0 ohm resistance. And in such a case, we can actually combine these 2 nodes into one another because the electric potential at both nodes at the bottom and the electric potential at both nodes at the top is identical. And because this is the case, we can shift the rightmost node into the center node, and we can do the same with the node at the bottom so that we get this changed circuit on the right side, which behaves absolutely identical in all aspects, but the key difference here is that we only have 2 nodes remaining, the node K1 and the node K2. And by reshaping the layout in such a way, we can now easily apply the junction rule by Kirchhoff to arrive at our derivation of the total resistance of this parallel configuration. And in order to do so, we can now apply the actual junction rule. We can compute the sum of all the individual currents entering the topmost node. We have I1 leaving the node, we have I2 leaving the node, we have I3 leaving the node, and we have I total entering the node, which leads us to this equation here. This is the application of the junction rule to the node K1, or to the junction K1 here at the top. And this can be used in order to get to a derivation of the total amount of resistance of this parallel configuration. And if you recall the video on Kirchhoff's first rule, this is the mathematical formulation of the law. The sum over all currents entering and leaving a node must obey or must be equal to 0. And this is the case here, which you can easily observe by computing the sum of all the components of all the currents leaving the node and look at the sum of the current entering the node. These are identical, which means that the Kirchhoff's rule applied to this topmost node provides the correct result. And we are looking for this particular equation here for the next step. And as you can see here now, we are applying Ohm's law to this sum of currents entering the topmost node. We can replace the total current entering the node by the ratio of voltage divided by resistance, and we're going to replace I total by the ratio of total voltage divided by total resistance. We can do the same for I1, I2, and I3, which yields these fractions here. First, the voltage across the first resistor divided by the value of the first resistor, the same for the second, the same for the third, equals 0. So this is still Kirchhoff's first rule applied to the topmost node, and we have used Ohm's law to enter these parameters instead of the individual currents. Now in the third step, we're going to exploit the voltage equality, because when you recall the video on voltage, you might also recall that voltage is a difference in potential between 2 points. So if we look at the colored version of this circuit here, this means that the simulation has added a color, and points of the same color also join the same potential. And green means high potential and gray means low potential. And as you can see across these resistors, we have a color gradient from green to gray, and this means we have a loss of electric potential across this resistor here. But if you look at the topmost node, this one here, this is green for all the resistors which join together in this particular node here, which means they share the same potential. The same holds for the bottom node, this node K2 here. All the connections to the lines leading to the resistors is colored in gray, which means they share the same potential. And this means that all the voltages sharing these two nodes are identical, because the difference of potentials is identical for all three nodes. And this means that U1 equals U2 equals U3 is identical to the voltage of the voltage source here on the left side, simply because this also joins these junction points here. And this means we can enter the same voltage here for all the different voltages which you have seen on the previous slide. So U total equals U1 equals U2 equals U3, and we now replace U1, U2, and U3 with the same voltage here, which offers us the possibility to divide by the total voltage on both sides of the equation, on the left and on the right, which is what we're going to do on the next slide. And as you can see here, we're going to isolate U total on the left, then we're going to divide by U total both on the left and on the right side, and what's left is the inverse of the total resistance, which is identical to the sum of the inverted individual resistances. And this can be reformulated. We can invert the left side, we can replace this sum of inverted resistors or resistance values by what's written here on the right hand side within the brackets, and then we can simply invert the result, which is the -1 here, and this is the formula for computing the total resistance of resistors which are connected in parallel. If you have n resistors which are connected in parallel, what you do is you sum up the inverted individual resistance values of all n resistors, and then you invert the result of this inner sum here, and what you get is the total resistance of the configuration. This is the formula which you can use in all the cases where you are looking for the resistance of resistors which are arranged in a parallel fashion in a circuit. Has shown. And in the last step, we're going to look at an alternative explanation despite or in addition to this mathematical derivation which we have seen on the previous slides. If you recall the video on Ohm's law, and previously we talked about this relationship between current on one side of the equation and voltage on the other side of the equation. Before we introduced the concept of resistance, we assembled a number of parameters here which are divided into geometric parameters, into material parameters. And these are, if the material does not change, constant. They are not of interest here because they are the same for both resistors, which are connected here in parallel. We have the elementary charge, we have the number of free electrons in a certain volume of the material out of which the resistor is made. We have the electron mobility, and then we have the cross-section area and the length of the configuration. And as you can see, when we combine these resistors in parallel, the length, the electrons have to move. One electron flows through the upper path, another flows through the lower path. The length through which they move across the entire length of the resistor is identical in both cases. It's not changed by this parallel configuration. However, what is adding up, and this can be better illustrated by looking at the diagram on the lower half of the slide here, what adds up is the cross-sectional area of these two resistors. This adds up. If the upper has the cross-sectional area A1 and the lower one has another cross-sectional area, the result is the sum of these cross-sectional areas, which can be combined in this geometric fashion. So A1 plus A2. And since this is the case, it becomes clear why combining resistors in parallel increases the surface through which electrons can move, and more surface area means less resistance because the electrons have more space through which they can propagate and move along and lose less kinetic energy due to collisions with atoms or other electrons within the resistor bodies. So increasing the surface area decreases the overall resistance. Now let's quickly summarize the most important takeaways for you from this video. Firstly, a simulation has shown that the total resistance in a parallel circuit is smaller than the smallest of the individual resistance values in this circuit. And secondly, the layout of a circuit diagram can be changed visually without affecting the functionality under some circumstances. And then the sum of the currents at a junction point combined with the Ohm's law provides you the basic equation for deriving the total resistance of a set of parallel resistors. And then the voltage drop of resistors connected in parallel is equal. This is a very important fact. If you connect two resistors which are placed in parallel, which share the node above the resistor and below the resistor, then the voltage drop across the resistors is equal, independent of the values which they have as resistance. And finally, the total resistance of such parallel resistors is the sum of the reciprocal values of the individual resistors to the power of -1. That's all from me for now for this video here. If you have any questions, leave them in the comment section down below so I can help you answer them, and I wish you a nice day. See you next time here on The Fearless Engineer.